Hello, my name is Irving Dai from MIT, and today I will talk to you about a joint project with Matt Hedden and Abhishek Malik involving Corks, Involutions, and Heegaard Floer homology. So firstly, let me thank the organizers for the opportunity to speak. And secondly, let me note that this is complementary to Abhishek's talk, which will be given in the four manifold section of this conference. So if you haven't already, please go watch that talk first, as it will contain a lot of topological background and motivations for the things that I'm going to be talking about. Okay, so let me first introduce the object of study. So what we're going to be studying is the homology Bordism group of involutions. Okay, this is denoted by theta tau sub z. And what this is generated by all pairs y comma tau, where y is an integer homology sphere and tau is an involution on y. Okay, and what we do is we mod out by the relation of homology cobordism with diffeomorphism. So in the setting, we say that y1 tau1 and y2 tau2 are homology cobordant if there exists a smooth homology cobordism between y1 and y2 in the usual sense. But now we require that the cobordism w come equipped with a self-diffeomorphism g, which restricts to tau I on the ends. Okay. Now note that G, the G does not have to be an involution. It simply has to be a self-diffeomorphism of W. Okay. And so again, I will refer to Abhishek's talk for connections between this object and the theory of quarks and strong quarks, which was sort of the motivation for this project. But for us, we'll simply take this as an object of study. And so the goal of the talk will be to define two Floer theoretic invariants of theta tau sub z. And these are going to be called h sub tau and h sub iota tau. And these will actually be group valued invariants. So they'll be valued in a certain group called the local equivalence group, which I will define for you. And actually, it turns out that they're homomorphisms. They're homomorphisms from this homology Bordism group of involutions into this mysterious group script J. And what I want to do is I want to sort of give an overview of the definitions of what these are. I want to do some simple examples for you. And I want to try to show you that you can do computations using these examples, using some formal properties of this group here, and also some simple topological constructions. Okay. So before I get into the definition of h tau and h sub iota tau, let me briefly remind you of an auxiliary construction that we will need, which is the definition of involutive Heegaard Floer homology. So this is due to Hendricks and Manolescu. And what this is if you give me a integer homology sphere y, then I can hand you back the usual Heegaard Floer complex CF minus of y. But it turns out that there's an additional bit of data which sort of comes along for the ride, which is a homotopy involution iota. Okay, so homotopy involution means the iota is a chain map from CF minus to itself. It doesn't quite square to the identity, it squares to the identity up to homotopy. Okay, so Hendricks and Manolescu defined this homotopy involution iota, and they showed that this pair up to the appropriate notion of homotopy equivalence is a well-defined three-manifold invariant of y. Okay, and for us, the most important property will be the behavior of iota with respect to the cobordism maps in Floer theory. So specifically, if W is a cobordism between two integer homology spheres y1 and y2, and S is a spin C structure on W, then you could ask whether the cobordism map associated to W and S intertwines the two iota actions at the ends. And the answer is that it almost does, except that I have to conjugate the spin C structure S. Okay. Now note that if S is self-conjugate, then of course FWS does indeed intertwine the actions of iota 1 and iota 2. Okay. And in particular, note that if W is a homology cobordism, then of course there's only one spin C structure and it is necessarily self-conjugate. Okay. So we formalize this in the following set of definitions. So the first definition I want to give you is the definition of an iota complex. An iota complex is just something that looks like the Heegaard Floer homology of an integer homology sphere together with the Hendricks-Manolescu homotopy involution. So the second bit here is saying that iota is a homotopy involution on C. And this first bit here is just the usual structure result for the Floer homology of an integer homology sphere. Okay, so just if y is an integer homology sphere, then the pair CF minus of y together with that involution, homotopy involution iota is an iota complex. Okay, and the second very important definition is the following notion, which is local equivalence. So C1 iota 1 and C2 iota 2 are said to be locally equivalent if there exists grading preserving chain maps F and G between them, such that firstly, if I look on the level of homology and I invert the action of U, F and G are isomorphisms. And secondly, F and G have to play nicely with iota 1 and iota 2. Okay, so if you've never seen this before, this first condition here just says if I look on the level of homology, then F and G map U non-torsion elements to U non-torsion elements. Okay, and we'll do an example to illustrate the notion of local equivalence in just a moment. Okay, but as you can probably guess, the point of local equivalence is just that if I have a homology cobordism between y1 and y2, then because of the intertwining property that we discussed earlier, the Floer cobordism maps associated to that cobordism give the maps F and G in the definition of a local equivalence. Okay, so if I have, so that means, so the point is local equivalence is sort of the algebraic analog of homology cobordism. It's just what I get in Floer theory from the homology cobordism maps. Okay, so we can sort of package this nicely in the following object, whose definition is due to Hendricks, Manolescu, and Zemke, which is I let script J, so this will be our local equivalence group that I discussed earlier, just be the set of all iota complexes, all possible iota complexes, and I mod out by the relation of local equivalence. Okay, and it turns out that this set has a group structure which is given by tensor product. And what we've said before is quite literally that if you give me an integer homology sphere, then this pair CF minus of y together with iota, the local equivalence class of this pair is a homology cobordism invariant. And in fact, Hendricks and Manolescu and Zemke proved that actually this assignment of this class constitutes a homomorphism from the usual homology cobordism group into this local equivalence group. Okay, so you can use this to attempt to study theta 3z, which many authors have done. But for us, well, okay, so let me do an example first, just to make sure that we all understand sort of the formalism. So on the left here, I've displayed the Heegaard Floer homology of S3. Okay, so the Heegaard Floer homology is very simple. It's just one F adjoin U tower, and there isn't much room for an involution on this homology. It has to send this generator to itself. Okay, on the right, I've displayed the Floer homology of sigma 237. So the dots represent generators over F, and vertical lines represent multiplication by U. So the Floer homology of 237 has two generators in grading 0, and if I multiply them both by U, they become the same generator in grading -2. Okay. And the action of iota on this Floer complex, I'm just going to assert it interchanges these two generators in grading 0. Okay, so this is a non-trivial calculation, but I will ask you to commit it to memory. This is sort of the simplest possible non-trivial calculation in evaluative of Heegaard Floer homology. Okay, and the question of local equivalence is the following question. We ask, are there iota equivariant maps between these two homologies which take U non-torsion elements to U non-torsion elements? Okay, so technically I should ask this question on the level of chain complexes, but I'm going to be a little bit sloppy and talk about the being on the level of homology. So, so the answer to this question is no. So for example, if I look at the right-hand side, well, I can map the right-hand side into the left-hand side by sending both V and iota V to X. And that's an iota equivariant map, and it maps U non-torsion to U non-torsion, so that's totally fine. But if I look on the left-hand side, if I try to map the left to the right, then I discover that I can't do that. Or I can't do that while at the same time satisfying the two conditions in the definition of local equivalence. So in order for the map to be iota equivariant, I would have to map X to either 0 or the sum of V plus iota V. Okay, and neither of those elements are U non-torsion. Okay, so what we conclude is that these two complexes are not locally equivalent. And therefore, S3 and sigma 237 are not homology cobordant. Okay, so I mean, this is sort of a very old result and can be proven many different ways. But let me take a moment and sharpen this a little bit by introducing the following definition. So if there exists a map F, as in the definition of local equivalence, in one direction, so remember in local equivalence we had to have maps F and G between these two complexes. If there exists a map F in one direction, then we write C1 iota 1 is less than or equal to C2 iota 2. And of course, if the map is in the other direction, then they're locally equivalent. So this becomes an equal sign. Okay. And so this defines a partial order on the local equivalence group. Okay. And what this example is saying, and what I want you to remember, is that sigma 237 with the Hendricks-Manilescu homotopy involution is strictly less than S3. Okay, that is to say, there is a map from the right-hand side to the left-hand side, but there is no map from the left-hand side to the right-hand side. Okay, so sigma 237 is strictly less than sort of the trivial complex. Okay, so this is a slogan which will become sort of important in an example which we will do at the end of the talk. Okay, so what do these ideas have to do with the homology Bordism group of involutions? So our strategy will be to utilize the action of the mapping class group on Heegaard Floer homology. So this was developed by Juhas Thurston Zemke and then developed to completion by Ian Zemke in a series of papers. And the naturality properties of Heegaard Floer homology are the following. So if I have, say, an integer homology sphere and a self-diffeomorphism f of y, then f actually induces an action on the Heegaard Floer complex CF minus of y. And the claim is that this is a well-defined action up to homotopy equivalence. And moreover, if f is an involution tau, then actually the induced action is a homotopy involution on CF minus of y. Now, if you know a little bit about Heegaard Floer homology, then you know there are some subtleties, which I'm gonna gloss over. But once again, now the question is how does the induced action behave with respect to cobordism maps? And here's where we are going to see the connection between the homology Bordism group of involutions. So suppose that W comma G is a cobordism from y1 comma tau1 to y2 comma tau2. So that is to say, G restricts to tau1 and tau2 at the ends. And let S be a spin C structure on W. Okay. So then you could ask, well, does the Floer cobordism map associated to W and S intertwine the induced actions of tau1 and tau2? Okay. And the answer is, once again, it almost intertwines them, except that I have to push forward the spin C structure S along this self-diffeomorphism G of W. Okay. So of course, if I can find a spin C structure which is fixed by G, then the Floer cobordism map associated to that spin C structure will indeed intertwine the actions of tau1 and tau2. Okay. And once again, note that if W is a homology cobordism, then this condition is vacuous because there's only one spin C structure and it isn't necessarily sent to itself under any self-diffeomorphism. Okay. Now, as an aside, again, what I said is not quite true, but I will gloss over some technical details for the purposes of this talk. Okay. So what this leads to is the following very straightforward idea, which is that because of what we said before, if I have y and an involution tau on y, then I get a homotopy involution, which I'm also going to denote by tau on CF minus of y. And the local equivalence class of this is a invariant of this class y comma tau in the homology Bordism group of involutions. Okay. And actually, if I not only have the induced action of tau, but if I compose tau with the usual Hendricks-Manilescu homotopy involution iota, I get another homotopy involution on CF minus of y. And this class is also, the local equivalence class of this class is also an invariant of the class of this in the homology Bordism group of involutions. So to summarize, I have three, and it turns out that these are sort of, as you might expect, these are homomorphisms. So I get three homomorphisms from theta tau z into the same algebraic group script j. Okay, now of course only the latter two of these h tau and h iota tau care about the presence of the involution tau. H exists, of course, regardless of the presence of the involution of tau. Okay, so these are the invariants we will use to try to study theta tau z. Now, what I've said is mostly just a formal, is sort of a formal consequence of the work of Hendricks, Manolescu, and Zemke, and also the naturality properties of Heegaard Floer homology. But the trick is really how can we compute these invariants h of tau and h iota tau? And the answer is that we're going to use the partial order, the fact that this group J has the partial order that I discussed previously. And there's sort of a very silly sounding observation, which is that suppose that I can compare y1 tau 1 to some other y2 tau 2. Suppose I know I have some inequality of h sub tau complexes. And suppose that I know that h sub tau 2 y2 is strictly less than 0 for some reason. Okay, then of course I've bounded h sub tau 1 of y1 away from 0, and then I can conclude that at least it's a non-zero class in theta tau z. Okay, and a similar statement holds if I know the corresponding inequalities for the h sub iota tau invariants. Okay, so the question then becomes, does that partial order in script J have any topological interpretation? Okay, so can I somehow know when I get such an inequality? Okay, so this will be the focus of this theorem. Suppose that W is a negative definite cobordism from y1 tau 1 to y2 tau 2, and W comes equipped with a self-diffeomorphism G, which restricts it to tau I at the ends. And let's say B1 of W is equal to 0. And assume for the moment that W, the intersection form of W is diagonalizable over the integers. So it's just a direct sum of minus ones. And let S be a spin C structure on W whose first Chern class has coefficients plus or minus 1 in the diagonal basis. Okay. Then there are two sort of nice situations. So the first is, suppose that S is fixed by G. Then I claim that I get an inequality of H sub tau invariance. And suppose that S is conjugated by G. Then I get an inequality of iota composed tau invariance. Okay. And the reason is very simple. I mean, if you think about the definition of local equivalence, basically the first condition in local equivalence is what I get out of a negative definite cobordism. Right? A negative definite cobordism map in Floer theory maps U non-torsion elements to U non-torsion elements. Okay, so if in addition G fixes this spin C structure S, then FWS will intertwine the actions of tau, and I will get sort of the map F that induces this inequality. Using FWS, that will be the map inducing this inequality. On the other hand, if S is conjugated by G, well then FWS doesn't intertwine the actions of tau, but it will intertwine the actions of iota composed tau, because tau will commute with this, except I have to conjugate S, and then iota will commute with this, except I conjugate S again. Okay, so FWS will intertwine the actions of iota tau, and I get this inequality here. Okay. Now let me just make a brief note. So the condition on Q sub W is required because I need the Heegaard Floer cobordism maps to have 0 grading shift. Okay, and here are some sort of very silly sounding special cases of this theorem. Suppose that W, the intersection form of W is just -1. So there's only one generator of the second homology, which let me call it X. So if G fixes X, if G acts on the second homology as the identity, then we get the inequality of H sub tau invariance. If G acts on the second homology by negation, then I get an inequality of H sub iota tau invariance. Okay, and I will call such a cobordism a -1 cobordism. Okay. Here's another very simple situation. So suppose that the second homology of W is generated by two elements, and suppose that my diffeomorphism G interchanges these two elements X and Y. Okay, so then I claim that I have inequalities of both H sub tau and H sub iota tau invariance. And the reason for this is very simple. I just consider two different spin C structures, X plus Y and X minus Y. And so G will fix this spin C structure, and it will negate this spin C structure. Which will give me the two desired inequalities. Okay. So now let me do some examples for you and try to show that this formalism can be. There's some nice simple topological constructions which sort of correspond to this formalism. Okay. So here I've drawn an example of a class in the homology bordism group of involutions. So here I have +1 Sergio on the Stevedore knot. So this is an integer homology sphere. And in fact, this integer homology sphere bounds a contractible manifold. Okay, and here I've drawn an involution on that integer homology sphere, which is given by 180-degree rotation around this axis tau. Okay, and so you can check that the symmetry of the Sergio picture extends to a symmetry of the Sergio manifold. So the question is, can we understand or compute the invariance of this y1 and this tau? Okay. In particular, let's say, can we show it's non-zero? Okay. So what is the strategy? Well, the strategy is to construct a negative definite cobordism from this manifold to some other manifold, which we better understand. Okay. And the cobordism in question will actually be simply attaching a single two-handle with framing -1 around this green curve right here. Okay. And note that this is an equivariant handle attachment. And as you can guess, the involution on y1 is actually going to extend over this handle attachment cobordism. Okay. Now, what do we get on the other end of this cobordism? Well, you can see that if I blow down this -1 curve here, what I will get is this +1 Sergio on this knot, which is in fact sigma 237. Okay. So what we have is we have a negative definite equivariant cobordism from this 3-manifold with involution to this 3-manifold with involution. Okay. And so we get some inequality of invariance. So which inequality do we get? Well, what we have to do is we have to determine what does the extension of tau does on the homology of the cobordism. Now, if you think about what happens here, if you think about the core disk of the attaching two-handle, tau acts on the boundary of that disk, this green circle, by an involution with 2 fixed points. Okay, and if you think about it a little bit, you'll see that that means that the extension of tau will actually reverse orientation on the core disk of the attaching two-handle. And actually, that means our extension of tau will act by multiplication by -1 on the second homology of this cobordism. So what we will end up getting is an inequality of iota tau invariance. Okay, so now we see that this is sigma 237, and we can get a little bit excited because, as you know, I gave you that other example of sigma 237. At least the Hendricks-Manolescu homotopy involution was strictly less than 0. So maybe this homotopy involution iota composed tau also gives a strictly less than 0 class. Okay, so how could we prove that? Well, now the game is to understand this example. So this is just the same picture as before. Okay, how do we understand this example? Well, it's the same game. So let me construct a equivariant cobordism out to a manifold that I understand. So if you see that we attach a +1 curve here, what I get on the other end will be S3. Okay, and this is, again, an equivariant cobordism. And of course, if I turn this cobordism around, it will be a negative definite cobordism with intersection form -1. Okay, so what that, and you can check that in this case, how does the extension act on the second homology? Well, the core disk, tau acts on the boundary of the core disk by 180-degree rotation. Okay, so actually you can show that you can show that this proves tau acts as the identity on the second homology. So what we do is we turn this cobordism around, and we get an inequality 0 less than or equal to h sub tau of sigma 237. But there are only 2 possible involutions on the complex of sigma 237. One is the Hendricks-Manolescu iota action, which is strictly less than 0. And the other is the identity, which is locally equivalent to the trivial complex. Okay, so actually this inequality forces tau, the action of tau, to be equal to the identity action on the Floer complex of sigma 237. Okay, and in particular, that means h sub iota composed tau is equal to h sub iota, which is strictly less than 0, which proves that over here we have this is strictly less than 0, and so h iota tau of y1 is strictly less than 0. So in fact, using the h sub iota tau invariance, this class is non-zero in the homology bordism group of involutions. So in fact, if you listen to Abhishek's talk, this proves that this example is a strong quark. So I believe previously it was not even known that this example was a quark. And as you can see, all we did was use some formal properties of our invariance together with an understanding of sigma 237 and some very, very simple Kirby calculus. Okay, so let me also quickly go over one more example. So this here is +1 Sergio on the -3, 3, -3 pretzel knot. with an involution tau. So this is in fact the original example of a quark due to ACT-BLUT. And we will reprove here that it is a quark and in fact show that it's a strong quark. So again, what do we do? Well, we just construct a negative definite cobordism out to a manifold that we understand. So in this example, we'll just attach this time two handles, -1 frame 2 handles around these green curves here. Well, what do I get on the other end? Well, actually, if I blow these down, then you see I get this +1 on this knot. This is again sigma 237. Okay, and in fact, this time I don't even really care what the action of this tau involution does on sigma 237, because this is a -1 interchange in cobordism. So this negative definite cobordism gives me an inequalities of both sets of invariants h sub tau and h sub iota tau with sigma 237. And one of those is necessarily strictly less than 0, simply because there are only two possible involutions on sigma 237, and they are related by the Hendrix-Manolescu homotopy involution. Okay, so I think I will stop here, and thank you for your attention.